questions by any chance?
Physics 1. Let me pull them up. I did get to them. Physics.
Well, what are you doing that? I'll just get my other gadgetry. And here we go.
Here we go. Oh yeah. We went over the physics homework. This one, if I recall, the cameras and.
Just remind me. Hang on. Let me just check here. It may be me that is that. Did we go through that one? We did. Maybe did we? Let me just. Check.
Yeah, we did go through the physics homework.
Okay. Okay. Now I think possibly Turing there was. That's fine if we went through it. I'm just trying to just check for my own sake here. I know that we went through some of the questions. I'm just not sure whether we went through all the questions. Did we go through all the questions? Remind me. Possibly.
We did not go do all of them. I think we did a good chunk. I think we went down to
articulates.
I think we stopped before 4.
Yeah, possibly. I'm just looking at this just before 4. So we looked at this one here. Okay, uniform ruler. Yeah, I remember looking through this, going through that. Yeah. And you've got those notes. Brilliant. Okay, good. And then I see your point. I see what you're saying to say. We would have then. So that was the last. Yeah. So after we had the homework, you would have then had. Yeah. The one with the camera boom and everything. Yeah. And we possibly, as you said, would have probably stopped shy of 4. Okay. Now, if you've not had a look at 4 yet, number 4, I would like you to, is that something you've done already or not yet done? 4 and 5.
4 and 5.
And 6 as well. So there's 3 questions. Are those have you looked at those already?
No, I have not done those. I did up to 3, the ones we went over.
Up to 3, yeah, that makes sense. Okay, so do you want to have those 4, 5, and 6 as homeworks that you can go through in your own time? Is that because then we can have time to go through a slightly newer topic today? Is that something you can do prior to our next physics lesson, you reckon?
Yeah, because I'll get refreshed and then I can go through everything.
Yeah, exactly. So I'm going to give you some time to, well, about a week or so really before we have physics again, because chances are on Thursday, you might want to go through a different subject, perhaps.
Chemistry, yeah.
Chemistry, you want to go through chemistry, I thought so. So it won't be until at least next week before we go through physics. How's been the start of your week at school? Have you been given a bit of a timetable when your exams kick off?
Yeah, they'll kick off at the very end of this month and they'll end right before Valentine's Day.
Oh, wow. Okay. So we don't have much time to play with. So we're going to try and make as much, cover as much ground. Okay. So end of this month, just looking at dates here for my own. So we're talking 31st probably, because the 31st is a Monday as opposed to the 24th. That would make sense. So 31st of Jan. So mock start date. Okay. All right. Okay, right. So moving on then with moments and really finishing off this topic, okay? So what are the key things that we have learned first? The 2 principles in physics that are worth remembering when it comes to moments. So moments are strongly linked to forces. And we say that for a body to be in equilibrium, there are 2 conditions. So for a body to be in equilibrium, the sum of all forces in every direction must be 0, but also the sum of the anti-clockwise moments must be equal to the anti-clockwise moments, okay? So if I had to draw a little diagram, if there's 20 newtons there, I'm going to need 20 newtons there. And of course, if there's 50 newtons up there, I'm going to need 50 newtons up there. So in every direction, the forces are balanced. Okay, so that is the first condition. I'm using a diagram here. The second condition is that if this is pivoted, yeah, the moments that are wanting this to spin that way, so we can say this is 10 Newton meters, must be equal to the moments that are trying to make it rotate that way, which is 10 Newton meters. So these two conditions have to be satisfied. The turning moments have to be equal and the forces in opposite directions have to be equal. Okay, good. Now this idea of center of mass, also known as the center of gravity. Now, we already covered a little bit of this when we first started looking at this concept of moments, because we were introduced with a term that is known as something. When something is uniform in physics, it means it's got a place where you can pretty much work out or figure out where the center of mass or the center of gravity is. So what is the center of mass? What is the center of gravity? How do you define that? What might you say to answer that one, Thierry?
It is like the equal point where like the weight could be held, like where it could be balanced.
Yeah, you're
So
absolutely
on
right.
both sides, the weight would be equal. And like the counterclockwise and
Would also be balanced. Moments,
yeah,
right?
would be
So the word here
balanced.
is moments, the turning
Moments.
moment. Okay, so the turning moment, you're right. So the turning moment, good. Now we can also say, define it differently as the place or the point where all the mass appears to be concentrated in an object, because it balances from that point where all the mass appears to be concentrated. Now, it's also known as the center of gravity. In other words, you can think about it as the point, the single point where gravity appears to be acting. And that's why it balances, because that point appears to be the point where the weight is acting through. So far, so good. Yeah,
Yes.
good. So center of mass and center of gravity. At this stage, I will tell you that they pretty much mean the same thing, but when you do advanced physics later on, you will notice that there's a slight difference. But for now, we're not going to bother about those differences. We're just going to bother with the idea of the center of mass and center of gravity, and then how we can use it to answer a variety of questions, okay? So, center of mass, how can we find the center of mass? Firstly, of something, say like a uniform ruler. Okay, so for a uniform ruler, e.g. a uniform ruler, where would we locate the center of mass? If the uniform is the ruler is uniform, it would be halfway, wouldn't it? In other words, you can also think about this. If you joined the vertices with straight lines, okay, so these are my vertices, two vertices joined and two vertices joined. It's the place where these diagonals would meet if this is a uniform ruler. You can also think about it as if I drew another line of symmetry, yeah, if I draw the lines of symmetry and see where the lines of symmetry intersect, that's another way. So if I drew, that's a line, the brown line is a line of symmetry, yeah? In other words, that's a mirror image of the other, if you remember learning about symmetry. If I drew another line of symmetry, where the two lines of symmetry intersect, if it's a uniform ruler, for example, gives me, or if it's a uniform 2D shape, gives me the center of mass. So this here would be my center of mass. What about if I was given a point such as a triangle? How would I find the center of mass of a triangle such as this? What would I have to do? Well, very similar to what we've done, but here you'd be looking for the angle bisectors. Now, remember having learned about bisection of angles or of lines? Have you learned that before? To bisect a line, yeah, and that is 2 divided into 2 equal parts. So if I bisect this angle and I divide it into 2, and through that I draw a line, and I go up to the other angle, and again I split it and I divide it into 2. So bisect it. And again, I go to my other angle and I do the same and I bisect that angle like so. Where these points will meet or intersect, this here will give me the position of my center of mass or center of gravity, okay? Now, why do we need to know the ideas about center of mass and center of gravity? Well, because they help us understand things like stability. So when you're designing something, knowing the stability is pretty important. And also, once we know where the center of mass is, then we can always then undertake calculations to work out how the moments are going to affect that particular object if, say, certain forces were acting on it. So this is for uniform shapes, okay? So a uniform rectangle, uniform square, uniform triangle. This is the kind of procedure you would carry out. But sometimes you have an irregular. What about if you have an irregular lamina? Now a lamina, what I mean by an irregular lamina, a lamina is effectively a 2D shape. That's what a lamina is, effectively is a 2D shape, okay? There is 3 dimensions, but the other dimension is very thin, that you can think about it as being a 2D shape. What about if my object was irregular? So here at the moment, we've been looking at regular objects, yeah, regular laminas. So I'm gonna call these here regular laminas. Shall we just call them regular laminas? In that they are well-known defined shapes, triangles, squares, rectangles, so on and so forth. Now here we're going to be looking at an irregular lamina. How do I work out the center of mass of an irregular lamina? Well, in this time around, I need to use a plumb line. Okay, I use a technique which involves using a plumb line. Do you recall using a plumb line? Well, what is a plumb line? A plumb line is simply a heavy mass that is attached at the end of a string. That is what a plumb line is, okay? Sometimes you also probably hear of the word plumb bob, okay? Plumb bob is the same as a plumb line. So in its essence, it's a mass attached to a string. Now, why are plumb bobs or plumb lines pretty useful? Well, for one, they can allow you to see if something is perfectly vertical. So one of the ways you can tell if something is perfectly vertical is, of course, you could use a spirit leveler, like the ones builders use. You've seen one of those before? Yeah?
Yeah.
But if you want to tell whether something is vertical, the other method you could use is use a plumb line. What does this mean? All you simply do is suspend a mass or a weight, yes, at the end of a rope vertically, and note that every time the string will always be in the most perfect vertical orientation. So in your exams, they like asking, how would you know that that ruler that is measuring, I don't know, some height is perfectly vertical, meaning it's perpendicular to the ground? How would you know? Well, the thing that we use is we use a plumb line. So stick a plumb line next to it, yeah? And if the plumb line hangs in the same vertical orientation, so that's my plumb line, by the way. I'm actually going to make it solid because it's very difficult to see. Yeah, there we go. So this is my plumb line. Plumb line, and this here would be my ruler. So if I wanted to check whether a ruler was perfectly vertical, check that it's aligned and in the same line as the plumb line. All right, so there we go. So plumb lines are pretty useful little things. So when you have your, with regards to your practical exam, Turin, are you going to do the alternative to practical, or are you going to do the actual practical exam?
You mean for the mocks?
For the mocks and for the final as well.
I know that for like the finals, it's like whatever like Cambridge told like my school to do, which I would think would be like the practicals. But then for the mock exams, our teachers are just kind of putting them all together. So no.
Okay, so what I'm okay, worth checking, because I think it's different because Cambridge do 2 versions of practicals. You can do one which is a written practical, so you don't actually have to go and use kit and instruments and be doing the practical. Then there's another practical which they do, which is the actual practical, which you actually have to be putting things together yourself in the lab in real exam time.
We don't put them together. We do the written.
Yeah. Okay. There we go. Okay, that's absolutely fine. When I was back in school, when I did my Cambridge International GCSEs, we also did alternative to practical. So it's quite commonplace to do alternative to practicals because it's a lot of equipment you have to get out. And unless
I would much rather do this than the written, though.
So you'd rather much do the actual practical itself?
Of course, yeah, you get something interesting.
It is. You're absolutely right. You're absolutely right. And things do sometimes go wrong, unfortunately, when you're doing the actual practical, and then you run out of time. So there's pros and cons to each one. But I think if your school has a very huge class, then it becomes harder for them to give equipment to each individual student. But where schools are slightly smaller, they tend to do the actual practical, okay? But this is one of the practicals here that you could have in your exam. So when you're finding the center of mass of something that is irregular, so an irregular lamina, how can we do it? Well, we can't just find lines of symmetry now. It's not as easy as that. We can't just bisect angles. It's not as easy as that because the shape is irregular. So we use this plumb line. So what you do is you put some holes in your lamina that you're trying to find out. So this is a hole A, that's another hole B, C, D. And essentially what you do is you hang your lamina off a clamp stand. Now, I will just draw this in slightly better fashion because this is not exactly showing the best picture. Blank page after current. So what you get now, Turin, just to give you a bit of a better view of this. So if you have your clamp stand like so. Okay, well, we know this is just a kind of easy picture of it. So you would place firstly inside there. So that's my holder. You would place your card. So that's the, so that you, if you want, even you can even think about this as a nail or, you know, the protrusion from your clamp stand. Now, what you do is you take your lamina. So that's my lamina here. That's my regular shape, by the way. So make sure that the shape, and this is my one of my holes, hole A. Now you're going to have other holes as well here, B, okay, C, and D perhaps, all right, just as an example. So make sure that this lamina can swivel freely, okay? So you don't want it being held or being too tight or there being a lot of friction between your hole and the support, all right? So that's your clamp stand. Then what you do is you put a plumb bob, plumb line, sorry, I should stick to plumb line. And you stick a plumb line at the very end. So this plumb line is fixed. It's not moving. So there you go, that's my plumb line. And what you simply do is you look at the line, if you like, the shadow line of this plumb line. So wherever this plumb line is pointing downwards, that is where you would also trace a straight line using your ruler. Then you hang it off B, okay? And you carry on with the same scenario. And what you should have now, you're going to have a series of lines, yeah, over which the plumb line was hanging. So this is now an end on view. So where these lines intersect, so you can see here, this was my first line I made with my plumb line, the dashed one. Now with the second position, which is at A, I'm going to have another dashed line, which I'm going to make. The point of intersection of these two lines will be the center of mass. And that is how we locate the center of mass of an irregular lamina. So far, so good? Yes. Yeah, okay. You've got the general idea. Okay, right. So now we're going to have a quick discussion about toppling because we said we're going to look at stability and toppling. So if we look at these two scenarios, we've got A and B. Which one do you think topples? Which one do you think stays upright?
Definitely A is gonna fall over.
Yeah, you're right. Why? How did you know that A will fall over and B will not fall over?
Because when you're looking at the red arrows, from like the baseline, you can see like the edge, and the red arrows over that edge, so you know that like it's gone to the point, like, you know, too far.
You're absolutely right, and there you go. You've got the physics absolutely right. For something to avoid toppling, you're absolutely right, Turin. Well done. Okay. So in this case, we can see that the center or the weight, look at the weight. This line represents the weight because the weight acts towards the center of the earth. It doesn't change its direction. It always acts towards the center of the earth. So in other words, if I was hanging a plumb line, the plumb line will always hang vertical, because it is being pulled towards the center of the earth. It can never hang in any other direction. So these arrows here represent the weight. The moment the weight gets outside the base of my object, the moment the weight is outside of the base of my object, there is a turning moment, a turning effect. And this turning effect causes it to topple. Here, however, yeah, there is also a turning effect. But can you see here the turning effect is in what direction? Here the turning effect is clockwise. Well done. And it falls outside of the base. Whereas the turning effect in this case is going to be anti-clockwise. Yeah, allowing this weight to fall within the base. So how do we improve the stability then? How can we improve the stability of an object? Well, if we lower the center of mass, it's going to take a bigger tilt, or you're going to have to give that object a bigger tilt before it topples. Okay. Also increasing the area of its base, because then again, it's going to take a lot more for the weight to appear outside of that base. So those are the two ways of how we improve the stability. Where do we see these typical features being incorporated? Well, when you look at Formula One cars, yeah, the typical design of a Formula One car varies significantly from that of the normal car that you drive on the road. Why? Because you need extra stability for those cars, but also things like extra streamlining. So they're particularly wide. Yeah, they're particularly wide, and therefore also have a low center of mass. And that is all to do with trying to keep that Formula One car stable at those high speeds. Okay. Then we look at other arenas where these issues become an issue. So double-decker buses. You got double-decker buses out there?
Oh.
No, nope. Haven't you got buses with two floors in Bishkek?
Nope.
No, all right. But you probably would have seen them in America?
Yes.
Yeah, of course.
In America, only a little bit in some places like New York. But yeah, I've been on one and I've seen them.
Yeah, okay. So you know exactly what I'm talking about. Okay, so that's my version of my double-decker bus. Okay, all right. There we go. And of course, it's got two regions. Okay. Now, the thing about these buses is that you cannot have, or when people do go up on the upper deck, they are advised not to stand. Why are people not allowed not to stand or advised not to stand in the upper deck? That is because if they're standing up, the center of mass of this whole bus shifts further up. And therefore, it becomes more unstable and likely to topple if it goes over an embankment or something that allows it to tilt. Okay, so passengers are advised, especially the ones who are at the top, to always be sat down. So as you get people in there, it's also going to change the center of mass. Also, another classic thing here is that as we add volume, so say imagine you've got, this is just an empty glass of wine, okay, and we've got one that's full here, same glass, but only this time we've put some liquid in it. Now, which one do you think is more stable, A or B?
I would say B.
Feels intuitively that B is stable.
Yes.
Yeah, it kind of feels that way. But actually, if you look at where the center of gravity for A is, it's around here.
Oh,
and if you look at the center of gravity where B is, it's about there.
Oh.
Okay, so which one is more stable, an empty wine glass or a full one? Well, the empty one is far more stable. Now, the reason why intuition tells you that B is more stable is because you're kind of thinking, I need to push this with a bigger force because it's got liquid in there. So part of your mind is thinking this is more stable because you need to push it with more force before it topples compared to A. But actually, A is more stable because the center of mass is much lower. So not your typical intuitive question, but something at least once you've seen it, hopefully you should remember it. So types of stability, okay? So we've got objects can be either in a very form of stable form of equilibrium. So these are here, I'm going to say types of equilibrium. If I just move this here, I'm just going to say types of equilibrium. All right, okay. So we have something known as stable equilibrium. Now, when we talk about stability, Turin, we always really look at what happens to the center of mass. The trick, if you want to work out what kind of stability, what kind of equilibrium, shall I say, we always look at what happens to the center of mass. So in this ball, here we go, the center of mass is located in the geometric center. Yeah, just as in any kind of regular shaped object, the geometric center will house, or if you like, is where the point where the weight or the center of mass will act. So if I raise this ball, what happens to its center of mass if I move this ball up? So it's in a bowl, it's in a kind of dish. If I move this sphere up to the point, what's happened to my center of mass? It's gone up.
In the ball, it moves up.
Yeah, it moves up. Yes. So it's still, so this is my ball here. So it's still located at the same place, but in terms of its relative position now, what's happened to the relative position of the center of mass?
It has gone up, yeah.
It has gone up. Exactly, you're right. So if I put that arrow there, so we can say here, C of M, meaning center of mass, okay? C of M has gone up. This, anytime the center of mass goes up, if you displace an object, if its center of mass goes up when you displace it, that object is said to be in stable equilibrium. Why? Because even when you let go and you release it, what's this ball going to do? Well, it's going to kind of oscillate to and fro, but eventually it's going to settle back where it came from originally.
Yeah.
So that is what we mean by stable equilibrium. It maintains its original position even upon being displaced slightly. And the key way to know is you always have to ask yourself, what happens to the center of mass? If the center of mass goes up, it means anytime you displace it, it means that when you release your force, that object will naturally come down to a lower will lower its center of mass. Therefore, it must be in stable equilibrium. In unstable equilibrium, however, now this time we have reversed the ball, the plate or the ball, if you like. So here's my sphere. That's my ball already. My dish is now inverted. Now, if I displace this ever so slightly, I give it a bit of a force, what's going to happen to my ball? It's not going to come back to this position, is it? It's gone. Yeah. So how can I tell that? Well, the one way to tell is you ask yourself, what happens to the center of mass? Now, can you see in this case that the center of mass has gone down?
Yes.
In terms of distance. This is telling you that this object is in unstable equilibrium. So C of M, center of mass, has gone down. Okay. Now, how can we check just every day, for example, if we look at everyday objects, for example, I might ask you, which one do you think is more stable? Bit of a trick question, this. A tricycle or a bicycle? Which is more stable?
More stable, I'm going to say, well, surface area is wider, slower, tricycle.
Tricycle, good. You've absolutely hit that nail on the head. So tricycle is more stable. So if tricycle is more stable, why don't we see more tricycles on the road? Why do we see more bicycles?
Maybe it takes like more energy to move the tricycle, or
yeah, you're right. In terms of energy, there's something there about energy that you've pointed out that is pretty useful there. Very good. Yeah. Anything else?
More uncomfortable.
Yeah, we can think of comfort, but actually what happens, right? If you look at what happens with a tricycle, this idea of stability got to be thought of in two ways. Now, if you try and turn a tight corner with a tricycle, if you try and turn a tight corner with a tricycle, and we're now going to compare that same turn of that corner with a bicycle, which one do you think is more stable as you take the turn, a tricycle or a bicycle? If you're going to make a tight
bicycle.
Bicycle is more stable. You're absolutely right. And it is for that reason that bicycles are favored. One of the reasons that bicycles are favored over tricycles. So tricycles are a bit unstable. So which means that when you're taking a turn, a tricycle's center of mass goes down. Absolutely. whereas the
Goes up.
bicycles goes up. And that's why the bike is more stable. So anytime, try and have a look at anything that is unstable in, think of any ideas where you know where things are unstable. You will notice that the reason why those things are unstable are that if you give them a slight push, the center of mass always goes down.
I see.
Yeah. And then of course, lastly, we've got neutral, I beg your pardon. Neutral is where the center of mass neither moves up nor down. So for example, now, if I displace this ball with a little force, all it simply does is we can see that the center of mass does not change height. The ball will simply move into a new position. This is what we call neutral equilibrium. So there's 3 types of equilibrium that you're going to have to know, which is stable, unstable, and neutral. Where do we see things where center of mass is being played with? And equilibrium? Well, we've seen some of these toys before. Yeah. So typically in a toy like this, you would not expect this to balance. Yeah. But such toys are well balanced. And here again, you've got 2 matchsticks. This is the rocking horse, and it's made to balance on a bar. You've got a bit of an iron nut. Now, why is this balancing? Why isn't it falling? Why isn't it toppling? The reason why is because in each of these cases, the center of mass is directly below the support.
Oh, I see.
And that's the reason why they don't topple. As long as the center of mass is within the base, then you know that no toppling is going to happen. Now, a key part here to add, Turin, because sometimes this is less intuitive, the center of mass doesn't always rest on the object. It can also rest outside the object. So if I had, for instance, here a shoe horse, a horseshoe, horseshoe. There we go. Now, where's the center of mass for this object? It's not going to be located anywhere.
I see, yeah.
This time around, so the center of mass doesn't necessarily mean the place where you can balance it. So it's a good definition to say where you can balance it. But for this particular object, the center of mass will be located somewhere here. Now, you can't balance a horseshoe from that position. It's impossible. Likewise, if you have a donut,
the center of mass is taken out.
Yeah, mass has been taken out in the middle. Where's the center of mass of this? It's located there, but you're not going to balance that donut from that position. So what we mean by the center of mass is better to say that the center of mass, because of these 2 examples, is the place where the weight appears to act. Okay, so in this case, the weight of this donut indeed would appear to act there, and the weight of my horseshoe here would also appear to act there. But I cannot prove it directly using, say, a balancing point, for example. Okay, so that's just something to keep in mind. All right, to say sometimes we do have the center of mass located on the outside of the object. It's not always that it would be on the main bulk where the mass is. Okay, so far so good.
Yeah,
excellent. So I'm just going to put a thing here, which is to say center of mass. Okay, right. Now, there is no teacher better than practice and you yourself getting involved, doing some of this and working through these problems. So what I'll do is I'm just going to bring up some questions that we can work through together. Yeah. Just a moment here while I do that. Let's have a look here. File import. Just going to import this very quickly. Go file, and then let's make sure we get the right one here. Yeah, it's the right one. Okay, beginning of a current flip chart. No. And what I'll do as well, Jared, is I shall send it via the chat as well. So if you want to open it directly on your PC, is that all right?
Yeah, that'll work.
Yeah, and then we can just go through them. So you've got better sight of the questions. Okay, Turin, where are we at? All right. Okay. Okay, that's winging its way over to you, Turin, and you should have a copy with you shortly.
Let's save it to download. Okay.
Have you got that?
Yeah, it's downloading and
Okay, just
done.
give it time, no problem.
Boom, open. Okay. Should I go through one and then go with you, or how many should I go through and then talk to you?
Yeah, we're just going to go through starting from question number 1, and we're just going to go through progressively and just see. We're just going to try and do as many as we can, really, as we work through the problems. Yeah, is that all right?
Yeah.
Okay, good. Now, some of them are going to be calculation. Do you have a calculator to hand?
Yes, I do.
You do, good man. Excellent. All right. So I'll just go back to minimizing this.
Diagram shows object of weight.
So these are all actual Cambridge International Examination questions.
Alrighty.
On the multiple choice part. But once we've done this, then we're going to move on to working out the long structured, the theory. That makes sense, okay? This, I believe, should state W of A is equal to, it's an equation, so it must have an equal to sign.
Let's see this time here. And number 2. No.
Okay, which one are you on to now at the moment, Turin?
I'm on to question 4 right now.
Oh, question 4, you're cruising. You are absolutely cruising, absolutely cruising. Shall we go to, all right, okay, good. I'll let you carry on.
Should we go through them or should we should I, like, do
Yeah,
them?
we can. I'll let you go up to the fifth question, and then we're gonna go through the first five, and then we're gonna see how well you've done on those ones, and then I'll let you progress. So yeah,
Alrighty.
cool.
Alrighty.
Okay, cool. All right. So let's go through the first five. See how you've got on. All right. So number one, what did you go for, Turin, for that one?
I got C
Good
W
man.
times A is equal to
Yeah,
Z.
absolutely. Excellent. Good stuff. All right. Top man. Number two.
Number two, I was not really sure how to find this, but I would write down B. I mean, not B. I'd write down C again.
Very good. Now let's go back to what you're absolutely spot on. What is the condition if we don't want something to topple? So this here,
The
these
base.
dots
So yeah.
represent the center of mass. The center of mass is where the weight acts. This is going through the base.
Yeah.
That's
Oh
going
yeah,
through
the
the base.
bases.
This is outside of the base. This is the base here.
Oh, okay, yeah.
So this has to topple, and it's going to topple this way. This here, the weight is still inside the base.
Inside.
So we always look at the base. The moment the weight is outside the base, toppling occurs. Okay? So well done. You got there in the end, and it was the best one to choose. Okay? So when you sometimes face situations like that, you can use elimination, isn't it? Because you probably looked at D and went, nah, that's not going to topple. That doesn't look like it's going to topple. That looks stable. Must go for C. Okay, good. All right. Number three.
Number three, I also picked C because if you like hung the plumbed like line,
yeah, it would. You're absolutely
it would
right.
Cross C.
You're absolutely spot on. Well done, Turin. Excellent. Okay. Number four.
Four, just like the way they worded it was a little weird, but I put D because each bag is worth 2 kg, and now it's worth 14. So yeah.
The way the worded is a bit weird, and sometimes Cambridge exams like to do that. Okay, number five.
Number five, I got A.
Number five, you got A. Smashing. So far, a perfect score. Do you want to press on and carry on with number six and the outstanding questions, please?
Sure, I'll go on number six.
All right, good man.
Six. So these numbers. Okay, so okay, diagram shows four objects on a flat surface.
Oops, I think. Sorry, Turin. Something just opened up here. That was not the game plan here. So where are the questions?
I have them up on my screen.
You've got them. Yeah, I'm just trying to bring this up. It's in here somewhere. Dear. Ah, we've got it.
Is a 1, 2 weeks.
Save as. Okay.
Number 10. Alrighty, I've done 6 to 10.
6 to 10. Good man. And let's just review through that. So for number 6, what did you have for that one, Turin?
I got A.
Good man. Yeah. Absolutely spot on. Excellent. All right. Top stuff. Number 7.
For 7, I got C.
Top man. Again, now you've absolutely understood the concept. No confusion. Yeah. Look out for the base. Top man. Okay. Number 8.
8, I got B.
You're smashing them. Excellent. Okay. Number 9.
9, I got C.
Top stuff. Smashing them. All right. Number 10.
10, I got D because the center of mass is lower and also has the one of the wider bases.
Very
or
good.
surfaces.
Absolutely. So they were checking to see, can you remember those two elements? Excellent. Okay, now hang on. This number 11 looks like the number 9, doesn't it? Which statement is correct? That looks like the number 9, I think. So we can cross out this.
Yeah, all the beams.
Yeah. So
It's
forget
the
about this
same.
one. That was the same as the number 9. Yeah. Okay, so we're gonna move on to number 12 then, shall we?
Sure.
So let's try and go for 12 until 15, perhaps.
Alrighty.
Let's see how we get on with those ones.
Wooden bar is pivoted centers. Alrighty.
Alrighty, go for it when you're ready, Taryn.
For
12.
12, I got B.
B, excellent, well done. Okay, excellent. Number 13.
13, I got C.
C, okay, now it says which diagram shows the rod in equilibrium? Now think about this. If this is pulling this way with 100 meters,
Oh, it's
and this is
that
doing
way,
this,
that way.
it's gonna rotate, isn't it? This is going to rotate. It's how you'd open a
Oh,
tab.
it would be A.
Spot on. Well done for
Should've
excellent.
put that one. I
Yeah,
tripped
but the
up.
whole thing of these questions are confusing, Turin. So I absolutely understand. Okay, in an exam, you'd have had time to go back to check the questions or go over them. Yeah, good 14.
B.
Very good. Absolutely spot on. Number 15.
I also got B.
Number 15, you got B. So if you look at this one, is the turning effect the greatest? Now, if that's the pivot,
Oh, I
got
also did the
shortest
same mistake.
distance. Yeah, so
I also
pivot
did the same. It
is the
would be
one.
A.
Yeah, so it's got to be
I need
A.
to write a note for that.
Yeah, make a note. You've got it anyway, so which is good. And did we see as far as number 15 only?
Yes.
Okay, brilliant. Which neatly brings us to the close of our session then, Turin. I'd like you to complete the rest of the questions from 16 to 20 to 27. Is that all right?
Yeah.
The multiple choice. And then when we then have physics next, we're going to go through your solutions and see how you got on. Well done today. How did you find that session, Turin?
Really helpful. Thank you.
Excellent, excellent, excellent. So we're going to try and work as best. Now, of course, Turin, would be worth knowing. I don't want to say that the topics coming in the exam because the teacher's simply going to tell you the spec. But maybe now that we've done moments, a nice thing would be to try and just catch up with them and say, right, I've gone through moments, center of mass, and all that kind of stuff. Are there any other topics that I missed out that are worth going through? So that next week gives us a bit of a chance to start putting up some of the pieces that we may need to focus on.
There will be one topic, and
Okay.
my physics teacher told me to talk to him tomorrow. And I do for chemistry this Thursday. We finished matter, right?
Yeah, we're finished matter, so we're starting a new topic. Which topic would you like?
I'm going into she said to go into and review organic chemistry.
Organic chemistry,
Just
yeah.
like we did a part of it. So
Yeah.
she just says like since like we just kind of did like a slight review on it because they did it like last year.
Okay,
So yeah, just to kind of go over it again.
I'll go through organic chem with you this Thursday. Worry not, okay? Fantastic. All right, I'm gonna rush off and go and teach some of your 12s, some electricity now, and I shall see you on Thursday, Terry. All right.
Yeah, have a good rest of the day. Hopefully,
You too. Cheers. Thanks again. Bye now, Terry. Cheers.
Have a good one. Bye.
You too. Thank you. Bye.